Hello students, this video lecture is going to cover the basic concepts on regression analysis, and this is also the last topic of your syllabus. Now let's start with the basic definition of regression. It explains the changes in dependent variable due to the impact of independent variable upon it. That means regression helps to predict the value of one variable based on the value of at least one or more than one independent variable upon it, and depending on the impact or effect of independent variable, the dependent variable basically reacts. Now in a linear regression model, the regression analysis relationship between a dependent and an independent variable is described by a linear function. For an example, if x is an independent variable which affects the dependent variable y, then y is assumed to be caused by x. And a linear regression population equation model can be written as follows, where y is equal to beta naught plus beta 1 x1 plus eta I, where it is represented in terms of one independent variable only, which is x1. Now the same thing can be represented in terms of two independent variables. So y is equal to beta naught plus beta 1 x1 plus beta 2 x2 plus eta I, where x1 and x2 are the two independent variables. And here one important thing to notice is, while we are trying to identify the impact of x1 on the dependent variable y, every other things remain constant. Similarly, while we are trying to identify the impact of x2 on y, then the impact of x1 is remain constant, so that we can identify their individual impacts on the dependent variable y. Over here, terms like beta naught represents the intercept of the given linear equation. Beta 1 and beta 2 are the population coefficients associated to the independent variables. These are also regarded as slopes, and eta I is the random error term. Now, the population regression line, if we write it in general form, instead of writing it in terms of describing the individual independent variables, so we write it as y is equal to beta naught plus beta I xi plus eta I. Over here, the beta I xi represents that beta and x can take infinite numbers. So I can be equal to 1, I can be equal to 2, I can be equal to 3, and that's how the equation can be extended. So in terms of a three variable equation, then we will write y is equal to beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x3 plus eta I. So that's how it goes on. Anyways, so as we know that we often don't work based on the population regression, population only, rather sometimes we rely on the sample as well. That's how, instead of a population regression line, if we write an estimated population regression line based on the given sample, then we will write the equation as yi hat is equal to b naught plus bixi plus ei. You can simply see the difference between these two equations. In the original population regression line or equation, the intercept is given as beta naught, and slope or coefficient associated to xi is given as beta I, and the error term is written as eta I. However, while we are writing the same equation in terms of a sample, then we are just replacing the y with yi hat, and instead of beta naught we are writing b naught, instead of beta I xi we are writing a small bi and small xi, and then eta I is replaced with ei, just to represent that this particular prediction or regression prediction estimation is going to be done on the basis of sample and not on the basis of population. So that's why we are differentiating between the two equations. Now, whether the model that I have already chosen is a well-fitted model or not, whether at all the independent variables will describe the dependent variables well or not. In order to study this relationship under regression analysis, we follow a measure of variation, where the total variation in the dependent variable is explained by the variation in the independent variable. The estimated population regression line is made up of two parts, where there is a regression sum of square part and there is a error sum square part. And these two combines and gives us the total sum of square. So that's why we have written that TSS is equal to RSS plus ESS. Now from this equation we can calculate the coefficient of determination, which is R square. And this R square is basically equal to RSS by TSS. And it represents, that means the R square value represents how well fitted the model is. By the model, I'm simply mentioning the regression equation line that we have already set, an estimated line, whether the x variables are going to represent the y variables correctly or not. Okay, so in order to understand that, we take in consideration the value of R square. Now the value of R square ranges between 0 and positive 1. You can obviously understand why it is between 0 to 1, because it's a R square, so the value can never be negative. Now if a coefficient of determination R square is close to 1, it represents that the model is very well fitted. If a coefficient of determination R square is close to 0, represents that the model is weakly fitted. And if the coefficient of determination R square is between 3 to 7, then it represents that the model is moderately fitted. That means that if the model is well fitted, that means the independent variables are being able to represent its impact on the dependent variable very well. And weakly fitted represents that the independent variables cannot at all or does not have an impact on the dependent variable at all. And moderately fitted means the independent variables can have a moderate effect on the dependent variable. So with all this knowledge in our mind, we are now going to perform a practical operation by using an Excel. We will be taking the help of Excel software, and we would like to identify the coefficient values of a given particular model. We would like to identify the intercept value. We would like to identify the correlation of the coefficient of determination R square, and finally we would like to form a regression line or equation from that particular model of example. So let's see it in the next video. Thank you.